Welcome to part 3 for chapter 11. We're going to talk about temperature and kinetics and mechanisms today. Now, you already have a general sense of temperature's effect on rates of reactions if you have used a refrigerator. Why do we keep things in the refrigerator? Well, because once food is exposed to oxygen and the environment, then reactions begin to occur that cause the food to go bad. And those reactions are slower in the refrigerator at colder temperatures. All right, so we know kind of a base point here that temperature does increase or decrease the rate of a reaction. So let's think about that on a molecular level. All right, when a reaction occurs, right, so let's make our statement here, right? So let's not be so aggressive with red. Okay, that higher temperatures are going to lead to increased rates. Okay, that's kind of what we're starting off with. So when we think on a molecular level, what must be true for a reaction to happen? Well, if two molecules are going to react with one another, they have to come into contact. They have to collide. But not every collision, and this is important, not every collision will result in a reaction. All right? What is important to recognize is that there is a minimum kinetic energy that is required for a successful collision, right? If our bar for success is an actual reaction. So how do we know if something's going to have a minimum kinetic energy? Well, that's based on temperature, right? We have looked at a Maxwell-Boltzmann distribution before, right? And this is going to show that when you've got a certain temperature, not every molecule is at that average temperature. There are higher energy, there are lower energy molecules. And so let's say that threshold minimum kinetic energy is at this arbitrary line here. Well, only a certain number of molecules you see in blue for the low T experiment, only a certain fraction of those molecules have enough energy to react. As you increase the temperature, right, you see that average temperature going up, the distribution is getting wider, and you've got more molecules now that have enough energy to react, right? So when you increase the temperature, what you're doing is you are increasing the temperature is going to increase the number of high energy molecules, right? And so that ultimately, it's more statistically likely that a collision is going to have a high enough energy to react, right? So that'll speed up the reaction. This minimum energy, right, is called the activation energy, this minimum kinetic energy. If we look at an energy diagram, we are going to be looking at something called a reaction coordinate, right? And it's kind of like a timeline. And then energy is on the y-axis. So even if you have an exothermic reaction, and there's a picture of it here. So you have your starting materials and your products. Now, if the products are lower in energy than the starting material, right, this is an example of something that's exothermic. But just because a reaction is exothermic doesn't mean there's no energy needed to get it going, right? Because as the bonds break, you are going to get a higher energy state. So you are going to go, let's try that again. You are going to go up and then down. This difference here is that activation energy, E sub A. All right, so if you see E sub A, that's your activation energy. And at this top point right here, the highest energy level, this is called a transition state. All right, a transition state, let's see if we can highlight right here. This point right here, this is sometimes denoted with this little double cross T. We'll make a little note here, right? So EA is activation energy. This little symbol stands for transition state, right? That high energy area is like right when you're in the middle of the bonds breaking or forming. You can't isolate them. They only exist very briefly, right? But they're always higher in energy than either the reactants or the products. And so that's that minimum threshold energy that corresponds to this line right here. So if you have molecules with enough energy that when they collide, they can get over that barrier, you will have a reaction. Let's see, you have that little transition state symbol there. It's also called the activated complex. Either one of those terms is fine. I'm just used to saying transition state. Now, that's not the only thing that's important. There's also some very practical elements you have to think about, and that is also just geometry, right? So you have to get a successful collision, it has to have enough energy, and it also has to be oriented correctly. So let's say we're taking this oxygen and reacting with N2O. Well, the new bond that forms is going to be an OO bond. And so if that oxygen hits the nitrogen side, it just bounces away. You don't get that reaction. But if it hits the oxygen, it forms a bond. So there's several things that are required for a successful reaction, right? Geometry and energy are both really important. The Arrhenius equation right here does show the relationship between the rate and temperature. Because you have your rate constant, and it is equivalent to A, which is called a frequency factor. It has to do with how often the molecules are colliding. But you see that you have E raised to the activation energy divided by RT. So because T is in the denominator of this exponent, higher temperature will actually lead to larger K, right? Which would be a faster reaction. Now, you're not going to have to solve problems with this for me, though it might show up in your homework. What I want you to note is R is that universal gas constant. I know it's in a different form. It just is different units. Instead of liter atmospheres, you have joules per mole Kelvin, right? When dealing with energy, this is an easier R value to use. Let's see, Arrhenius behavior. We're just going to continue on. I'm not going to ask you to solve a problem like this, so we're going to skip over it. What is a good connection to make, right, is this, it's called Arrhenius behavior, kind of combining everything we just talked about, right? The higher the temperature, the more molecules have enough energy to react. So if you have molecules that are colliding more frequently because they're moving faster, it's more likely that you're going to get the right geometry in some of those collisions because there's more of them. It's more likely that more of those collisions will have enough energy to react. So for for those two reasons, higher temperature is going to lead to a higher rate, right? And you see the difference here, right, between low temperature and high temperature. Your collision energy, there's more molecules that it's not going to be high enough. There's less collisions, so likelihood that you're getting the right geometry is lower. Higher temperature, both of those things are addressed. Okay, so for the last section, we are going to look at reaction mechanisms. Now, that reaction coordinate that we talked about from starting material to product, it isn't always that simple. Sometimes a reaction goes through several intermediates and different steps before it gets to products. And those steps are determined experimentally, and they're called elementary steps. So you can actually write rate laws for elementary steps because they are determined experimentally, and you can figure out which step is slowing a reaction down. It allows you to see the different intermediates and catalysts in a different way and get a better picture of, we're not just moving from starting material to product. What do we see along the way? So when we think about these elementary steps, there may be 1, 2, or 3 reactants, and we would call that unimolecular, bimolecular, or termolecular, right? So unimolecular will have 1 reactant, bimolecular will have 2, and termolecular will have 3. We're not going to go higher than that. 3 is already unlikely, because if you have an elementary step that requires 3 molecules to collide to react, then the likelihood of that geometry being correct and the energy being correct in order to form a reaction it's just not going to be as likely as unimolecular or bimolecular. Right? Now, we're not going to do this example. We're going to consider the reaction of 2 ozone molecules. Right, so I'm going to blow this up a little bit here. So we're going to have 2 ozone molecules, O3, reacting to form 3 molecules of O2. Now note this says via a chlorine radical. So this reaction only takes place in the presence of a chlorine radical. And this is a 2-step mechanism. All right, so in step 1, a chlorine radical reacts with O3 and gives us ClO radical and O2. In the second step, that ClO radical reacts with another molecule of O3 to give us Cl radical and 2 O2 molecules. All right, so this reaction is facilitated by that chlorine radical. The overall reaction, and I don't know, let's see if this says this up here. No. The overall reaction is equal to the sum of the elementary steps. So think about, like with Hess's law, we're going to add these 2 equations together, right? And we should get the overall. Now, when you add together, anything that's on both the left and the right, you're going to cancel out. So I'm going to go ahead and cancel out. I see chlorine radical at the start and at the end. I see chlorine oxygen radical on both sides. So when I go to add this up, I'm going to have 2 moles of O3 yielding 3 moles of O2. Okay, so this is a reasonable mechanism at least. A couple of things that we can point out here is both steps are bimolecular, right? The first step, you need a chlorine radical and an O3 molecule. And in the second step, a chlorine oxygen radical and an O3 molecule. And there's a few things that we want to point out that are characteristics of mechanisms. And this is just a chart of molecularity. Number 1, that is the reactive intermediate. You are going to see these in most mechanisms. The reactive intermediate is neither a starting material or a product. It is generated in one step and then consumed in another. So for example, in this one up here, the chlorine oxygen radical is a reactive intermediate. Right, we make ClO in step 1, we use it in step 2. It is not an overall product. Number 2, we're going to talk a little bit more about at the end of this lecture, but that is the catalyst. A catalyst is going to affect the rate. Again, we'll talk about that, but how do you recognize it in a mechanism? It is present at the beginning and it's unchanged at the end. So you do not consume the catalyst. Oh, goodness, pardon me. Now, in this reaction, that would be the chlorine radical, right? It's necessary. It's in step 1, we see right here, but it is regenerated in step 2. So overall, it's unchanged, right? You have it at the beginning, you have it at the end, it facilitates the reaction. So both reactive intermediates and catalysts are not present in the overall reaction, but one is there at the beginning and the end, the other is generated and then used up. And then the third characteristic, all right, we've already talked about, when added, right, the elementary steps, oh, I already wrote this, equals the overall reaction. Okay, well, I guess it bared repeating. All right. Now, let's take some of what we've learned and let's look at another mechanism and answer some questions. Some elementary steps can be manipulated, and we're going to see that here. So we're looking at this reaction or decomposition of dinitrogen pentoxide, and it is proposed that this occurs in 3 steps. One with the N2O5 breaking down into NO2 and NO3. Then the NO2 and NO3 reacting with each other to form NO2, NO, and O2. And then the NO and NO3 reacting to form 2 more molecules of NO2. Now, does this mechanism provide the correct stoichiometry as it is written? Well, to figure that out, let's add them together. So I see that I have N2O5. I see, what can we cancel out? NO3, NO3 on both sides. One of my NO2s will cancel out. One of my NOs will cancel out. And it looks like I am left with an NO3 on the starting material side. Let me pull this out. Okay, so I would still have NO3, and then on the product side, I would have 3 NO2s instead of 4, and O2. So not quite, not as written, but we could adjust it. The most obvious thing to fix is that we need 2 molecules of N2O5 for this to work. So if I just multiply that first reaction by 2, let's see what that does for us. All right, that gives us 2 moles of N2O5. And let's see, what cancels out? 2 moles of NO3 will cancel out with both 1 and 2 moles of NO3 on this side. Now we have 1 mole of NO canceling out NO. And the only thing we have to deal with now is NO2. Now on the left side, you have 1 molecule. And on the right side, you have 1, 2, 3, 4, 5. So 1 will cancel out 1 of them. But the other 4 will still be there, plus O2. Now that does give us proper stoichiometry. So this mechanism wasn't quite right, but it was easily adjusted by multiplying one of the steps by 2. All right, so here we go. Let's keep looking forward on this. Identify all the intermediates, right? So the reactive intermediates for this reaction would be something that's generated in the reaction, but you don't see it in the overall reaction. And that for this one would be NO and NO3. Right? NO3 is generated in step 1, used up in step 2. NO is generated in step 2 and used up in step 3. And neither one of them are seen in the starting materials or the products. Molecularity. Step 1 is unimolecular. And that's why it might be written this way initially. It is the breakdown of just a single molecule, and it is not relying on a collision. Step 2 is bimolecular. And step 3 is bimolecular. You would need to see this mechanism written out initially to know that that first one was unimolecular. Usually if you see two molecules, they are colliding. All right. How does the mechanism affect the rate? Well, for one, if you know the different steps, the slow step is the rate determining step. The overall reaction can only go as fast as that slowest step. And so knowing the order that the bonds are breaking and forming can help you identify that slow step. You can write rate laws for individual elementary steps, but overall reaction order still needs to be determined experimentally, like we saw in the first and second videos. The last thing that we want to talk about is catalysis. The catalyst, like we saw in this reaction over here, the chlorine, is something that will increase the rate of reaction, but is not created or destroyed in the process. Both of those things are true about catalysts. There are different types of catalysts, homogeneous and heterogeneous. Homogeneous just means it's in the same phase, right? With the degradation of ozone, the chlorine radical and the ozone are both gases. That would be a homogeneous catalyst. But there are lots of catalysts that are heterogeneous, right? And that lots of metal catalysts that are solid and your reagents are a liquid or a gas and they'll come into contact with the surface of the solid. That would be a heterogeneous catalyst. Okay, that was all I wanted. Those are just definitions that you should know. This is a picture of a heterogeneous catalyst reaction where you have this reaction between this blue and red, whatever this is. They adsorb onto the surface of the catalyst. That helps facilitate the bond breaking. They can then migrate to one another, form new bonds, and then desorb. Right? So that's just a picture of how a heterogeneous catalyst could work. And how does this actually speed up a reaction? How does it work? It speeds up the reaction by changing the mechanism, by changing the intermediates that are formed, by making them lower in energy, right? So they're going to, by changing those steps, they help lower activation energy. So you have a different transition state in the catalyzed reaction, and it's lower in energy, so more molecules can get over the hump. More collisions will result in a reaction, thus the rate will increase. The last section on process engineering we're not going to cover, and so that is the end of chapter 11. I will see you in chapter 12.